Hello, everybody. Welcome to today's crime seminar. Today we have two speakers, two talks. Our first speaker is Heechang Kim. He will be giving a talk on physics-informed Laplace neural operators, data efficiency, and out-of-distribution robustness. Heechang Kim is a PhD student in the Department of Mathematics at POSTECH, advised by Professor Min-Suk Choi. His research focuses on physics-informed machine learning and the optimization of neural operators. With that short introduction, the floor is yours, and you can start your presentation.
Hello, everyone, and thank you very much for the introduction. My name is Heechang Kim, and it is a great honor to speak at the Crunch seminar. Today, I'm excited to share our recent work, Physics-Informed Laplace Neural Operator for solving partial differential equations. And this is joint work with Chen-Ning Kao and Hyung-Min Shin, and Seung-Chul Lee, and Professor George Karnadakis, and Professor Min-Suk Choi. Here is a brief outline of today's talk. I'll begin with the background and motivation, and then I'll introduce our model, followed by two key design elements, virtual input and temporal-causality weighting. And after that, I'll present the numerical results, and finally, I'll close with the main conclusions and limitations and future direction. To set the stage, let me briefly distinguish pins from operator learning. As everyone here knows, pins are function approximator grounded in the universal approximation theorem. In contrast, operator learning approximate operators, meaning that they learn a function space to function space mapping. In this setting, an operator G maps the input field A to the solution field U. And the examples below illustrate the operator learning. And for Darcy flow, we map a permeability field to the Brittle solution. And for Burger's equation, we map an initial condition to the corresponding solution. And so, rather than solving each PDE instance from scratch, operator learning aims to learn a reusable mapping from varying inputs to solution fields. Operator learning methods are often divided into two major families, and the first is the Debonet family. Debonet, originally proposed by Professor Lulu, was motivated by the universal approximation theorem for operators. It uses a branch trunk architecture to encode the input function and the evaluation location, and then learns the mappings from inputs to solutions. And since then, many variants, including V-Debonet and W-Debonet, and even Debo-Mamba, have been proposed to improve efficiency and accuracy across various problems. The second major family is the neural operator family. At a high level, neural operators aim to learn a global nonlinear operator through the iterative kernel integration. And because direct kernel integration is computationally expensive due to the integral over the entire domain, so many neural operator methods mainly differ in how they make this step efficient. For instance, a Fourier neural operator uses Fourier transform to convert convolution operator into multiplication in Fourier space, which makes the computational much more efficient. In a similar spirit, the Laplace neural operator uses the Laplace transform, which can be seen as a generalized form of the Fourier transform. One of the key advantages of neural operators is that once trained, they can perform near real-time inference across many different conditions simply by changing the input field. This is especially valuable in engineering and design workflows because it reduces the reliance on expensive simulations and enables rapid design exploration and optimization. This is why neural operators have become highly active and impactful directions in AI for science and engineering. The figures below show a few examples. On the left is one of our industrial projects, and we predict the temperature field from the PCB configuration to accelerate the PCB design flow. The middle figure shows the use of neural operators for airfoil shape optimization. And the figure on the right shows that neural operators can also make predictions in practical engineering settings from sparse observations. However, neural operators have also important limitations. That the first is that purely data-driven neural operators usually require a large amount of paired simulation data. The plot on the left shows the test error versus the number of training samples. And as you can see, as the number of training samples decreases, the test error increases sharply and can even blow up. So in practice, when data are limited, the predictions can become much less reliable. One obvious solution is to generate more simulation data, but that is often unrealistic in the industry because high fidelity simulations are computationally expensive and scaling the dataset is not that easy. The figure on the right shows an example from one of our another industrial projects with precautionary simulation data from the POSCO Steelworks. And in that case, generating a single 3D simulation sample can take more than a week. Of course, there are other ways to address these data limitations, such as transfer learning and multi-fidelity learning. And however, in this work, we take another different route. So rather than trying to rely on more data, we bring the governing physics directly into the learning process. In short, when data are expensive or limited, purely data-driven neural operators may not be the best option. The second limitation is the out-of-distribution generalization gap. The heat map on the left shows the result when we vary the correlation length in training and testing. Along the diagonal, where the training and the test data come from the same distribution, the performance is good. But in the lower right region, where the model is trained on smooth data and tested on more oscillatory data, the error increases noticeably. So neural operators can work well in distribution setting, which means that the training and test distribution are same. But once the test distribution differs from the training distribution, their performance may degrade substantially. And this motivates the need for operator learning methods that are more data efficient and more robust to out-of-distribution generalization. To address these limitations, a natural step is to incorporate the governing PDE, that is, to introduce a physics-informed structure. Several such methods have been already proposed, including physics-informed DBONet and physics-informed FNO. While they improved over purely data-driven approaches, but they do not fully address the issues we focus on here. For example, physics-informed DBONet was mainly evaluated with training sets of around 1,000 to 10,000 samples, so it does not really target the small data regime. PyFNO does consider the small data regime, but it does not really explain in a systemic way that how or why the physics-informed structure helps when the data are limited, and its out-of-distribution evaluation is also quite limited. So overall, there is still room for a physics-informed operator learning framework that is more carefully designed for small data and out-of-distribution. So we propose physics-informed Laplace Neural Operator, which enforces PDE, boundary condition, and initial condition losses during training. So architecturally, it is built on an advanced LNO backbone and further enhanced with two training mechanisms. The first one is virtual input, and the second one is temporal-causality weighting. These are designed specifically to improve performance in small data and out-of-distribution regime. Before introducing the advanced LNO backbone, let me briefly recap the Laplace Neural Operator. LNO handles the kernel integration step using Laplace transform, and under the pole residue representation and after applying the inverse Laplace transform, the response can be expressed as the sum of transient term and a steady state term. In this formulation, the poles mu n and the residues beta n are treated as trainable parameters. And because this representation is more general than a purely Fourier-based parameterization, so LNO can capture transient responses and non-periodic functions more effectively than FNO in many settings. The Laplace layer decomposes the response into a transient term and a steady state term through the pole residue form. And thanks to this parameterization, so this parameterization is physically interpretable, and it helps LNO captures to non-periodic signals and reach transient dynamics more effectively than Fourier-based operators. However, in vanilla LNO, both transient and steady state components are tied to the same pole residue parameterization. And as a result, in deeper architectures, this coupling can become too restrictive and limit the representation of more complex dynamics. So to gain more flexibility while preserving interpretability, we keep the transient component in pole residue form and replace the steady state component with learnable Fourier multiplier. And we call this variant the advanced LNO. This idea first appeared in the supplementary material of LNO by Chen-Ning Kao, and here we provide a full mathematical formulation. On the right side, we can see in formula form that how FNO handles the kernel integration. The key observation is that the output of F Fourier layer exactly matches the steady state response term of the Laplace layer. So in other words, the steady state component of LNO is precisely the Fourier-based representation used in FNO. So we replace the steady state term in LNO with an FNO-style Fourier multiplier, and this makes the model more flexible while preserving interpretability because the transient part still keeps the pole residue structure. As a result, advanced LNO can match or even outperform FNO while providing greater expressive power for problems with rich transient dynamics. Now, let me introduce the problem setup and notation. We consider a general time-dependent PDE with possibly nonlinear differential operator n. We denote the operator by G, which maps an input A to the solution U. Here, A represents the PDE specification, including, for example, the PDE coefficient C and the initial condition U0, and the forcing or source term F. The output U is the corresponding space-time solution field. In operator learning, so our goal is to approximate this G with neural operator G theta. And for training, we assume that we have n paired training samples where AI is an input instance and yi is the corresponding solution. So the data loss is then simply the mean squared error between the model prediction and the reference solution yi. And this gives the standard data-driven objective, and we can add physics constraints on top of this baseline. And now let me introduce the Physics-Informed Laplace Neural Operator, or PILNO. We define three physics-based losses: the PDE loss, and initial condition loss, and the boundary condition loss. The PDE loss penalize the governing PDE, while the other two emphasize the corresponding initial and boundary conditions. And we can define the physics-informed loss as a simple weighted sum of these terms. And architecturally, the pipeline remains the same as the data-driven neural operators, so that we feed an input function A into the advanced LNO backbone and obtain the predicted solution field U theta. The difference is that during training, we use not only the data loss, but also these physics-based losses, all computed from the predicted field. So if we use only the data loss, then the model reduces to LNO. And once we additionally incorporate the physics-based losses, then it becomes the physics-informed LNO. This gives us a physics-informed LNO framework that improves physical consistency. And the point is, these PDE initial condition and boundary condition losses require only the model prediction itself, not the reference solution. Now, let me explain why we introduce virtual inputs. Of course, physics can help, but we need some careful consideration when adding a physics loss on the paired training data. The figure below shows the test error of LNO and physics-informed LNO across the number of training data. And as shown in the figure, when enough training data are available, physics-informed LNO outperforms LNO. But in that case, the data-driven model is already doing quite well, so the physics loss mostly behaves just like a regularizer or brings only limited extra benefit. However, the story changes in the small data regime. So if physics residuals are enforced only on the same small data set, the supervision is restricted to a narrow range of inputs, and that can lead to overfitting issues and somewhat rudely, even worse, the performance than the data-driven baseline. So this brings us the key questions that how can we make physics truly useful when training data are limited? And before introducing the virtual inputs, let me briefly explain why performance often degrades in the small data regime. The figure below is conceptual illustration of neural operators with sufficient training data set. When the training set is sufficiently large, the data covers the input function space fairly well. In that case, the test data usually lie within the region covered by the training data, so the test process can be understood largely as an interpolation problem. And fortunately, interpolation problem is usually where those deep learning models behave pretty well. However, when the training data are limited, they can no longer cover the input space sufficiently well. And in that case, the test data are more likely to fall outside the region covered by the training set. So the test process becomes something closer to extrapolation-like problem rather than interpolation problem. And in general, extrapolation problem is much more harder problem than interpolation. So from this perspective, we can understand that why performance tends to drop when the training set is small. And this motivates our next step, the virtual input, which let us extend the input space coverage via physics supervision beyond the limited paired data set. And the main idea is very simple, that virtual input helps turn a hard extrapolation problem into something closer to interpolation. In many PDE settings, generating a labeled input solution pair is very expensive, but just sampling a new admissible input is essentially free because we don't have to compute the corresponding reference solution. So we introduce virtual input, which is additional unlabeled input that broaden the training distribution. And by training the model on a wider range of inputs and enforcing physics constraints on them, we can make many difficult test cases look less like extrapolation and more like interpolation-like problem. And happily, that is usually a much friendlier situation for the model. As a result, virtual inputs improve performance in the small data regimes and also enhance generalization under distribution shifts. And let me make this a bit more concrete.
Hi, I have a question. My name is Kamal. How do you define the interpolation data or out of extrapolation for the multidimensional problem?
This is just a conceptual illustration for the function spaces. And so for the multidimensional problem, we roughly say that if there are sufficiently large data to cover those function spaces, then it would be okay. The performance is good.
So how do you decide that the X is inside or outside? Is there anything mathematically like possible to define for a like high dimensional problem, or just visualizing?
Because this is just a conceptual illustration, so there is no way to exactly defining the problem is interpolation problem or extrapolation problem, but it's just like explanations for those phenomena.
Okay, thank you.
Thank you.
I also have a question about the graph. So it looks like physics-informed plus Laplace Neural Operator performed worse on data scales regime.
Yes.
So could you please comment on that? Because you mentioned that physics-informed laws can be useful when data is scarce.
Yes. What I want to say is, of course, physics can help, but just naively adding the physics constraints to training data set can lead poor performance. And that's why we introduced the virtual input.
Okay, I see. Thank you.
Thank you. So we sample n virtual inputs, and for those inputs, we define physics losses in exactly the same way. So the total training loss is then written as follows. And this can be understood quite naturally from the perspective of pins with sparse observations. So where we have labeled data, we use the data loss to anchor the model. And elsewhere, we rely on the physics loss via collocation points. And from this viewpoint, a small data in function space in PILNO corresponds to sparse observations in space-time domain in pins, and the virtual inputs in physics-informed LNO corresponds to the collocation points to calculate physics residuals in pins. So to be clear, virtual inputs are not a completely new idea. So related concepts have already appeared in prior physics-informed operator learning methods. For example, physics-informed FNO considers sampling additional PDE instances such as new initial conditions or coefficient fields. So our claim is not that virtual input themselves are entirely new, but how we reinterpret and use them. So in our framework, virtual inputs are not just extra unlabeled samples. So we use them to deliberately broaden the input function space coverage and provide physics-only supervision for both small data learning and out-of-distribution robustness. So, and we also show that enforcing physics residuals only on a limited paired dataset can worsen overfitting. So virtual input helps address that specific failure mode. So in one sentence, we reinterpret the virtual input as an operator level extension of the collocation points in pin level. And we show that they can improve both data efficiency and out-of-distribution robustness when designed properly. Next, let me explain the motivation for temporal-causality weighting. And for time-dependent PDE, a vanilla pin can fail to capture the true dynamics. The figure on the left shows an example for the convection equation trained up to t⁵ seconds. And as you can see, the solution collapsed to a trivial solution. And the middle plot shows the training losses across the training epochs. And the plot on the right shows the residual at each time slices. And this happens because earlier and later time residuals are optimized simultaneously. And as a result, the optimizer can reduce the total physics loss by fitting later times to trivial solutions, while still leaving large errors at earlier times. This is known as temporal masking. In fact, both the residual loss and the initial condition loss appear to converge nicely in the middle plot. But the plot on the right tells that the residual near the initial time remains quite large, while the late time residual becomes very small. And importantly, the same issues can also arise in the physics-informed operator learning, because PDE losses are enforced over all time snapshots jointly, just as in pins. So for time-dependent PDEs, we need careful design for PDE loss that respects temporal causality. Some ideas have been introduced in the pin literature. One example is work of Saipan Wang and his collaborators proposed causality-aware weighting schemes that emphasize the early time residuals during training. And another example is Sin, which is actually one of our papers. And it addresses the same issues in a different way, using a time marching strategy instead of enforcing the full time horizon all at once. So together, these works motivates our use of temporal causality weighting as a practical way to stabilize physics-informed training for time-dependent PDEs. Now, let me show how we define temporal causality weighting in physics-informed LNO. The main idea is simple. So instead of treating all time steps equally, we give more importance to the earlier ones. So for a single input AI, the PDE loss can be reformulated as follows. So it is a sum of per time step residuals over the temporal grid. And concretely, we define a residuals at each time slice tk. And then standard PDE loss is simply the sum of these residuals across time. To enforce temporal causality, we introduce a positive and monotonically decreasing weight schedule WK, and this places larger weights on earlier times. So the model is encouraged to fit the early time dynamics first, which helps reduce temporal masking. Since this reweighting changes the overall scales of the loss, so we then normalize the weight to keep the loss magnitude stable. The final causal PDE loss is just the weighted sum of per time step residuals using these normalized weights. The recipe is quite simple, so we decompose the PDE residuals over time and multiplying the temporal causality weights and train with resulting causal PDE loss. Now let me give a more operator level view of why it is useful. This slide is better viewed not as a rigorous proof of PyAdeno's exact training dynamics, but rather as a motivational operator level analysis illustrating that why early time errors can be particularly important in time-dependent dynamics. Consider a discrete time flow map S delta t, and suppose we learn a one-step operator R theta that is applied repeatedly over a row route. At each step, we define the row route error EK as the difference between the predicted state and the true state, and the one-step defect as the mismatch between the learned operator and the true flow map. If we propagate the error forward, the next step error can be written as two parts, one coming from the current error through the dynamics, and the other coming from the one-step defect itself. When we unroll this recursion, we found that the error at the later time is essentially the sum of defect terms, each amplified by the dynamics of the subsequent steps. And in other words, early time defects can have disproportionately large influence downstream because they get propagated again and again. Under a local listage assumption, this intuition can be made precise. So the row route error is bounded by the term involving the initial error plus a weighted sum of one-step defects, where earlier defects receive larger effective weights. This is exactly the motivation for temporal causality weighting. If we reduce early time defects during training, we are in the best position to stabilize long horizon predictions. Of course, physics-informed LNO is not an explicit autoregressive rollout model, since it predicts the full space-time field in a single forward path, but our physics law still decomposes across time slices, so the same insight still applies. Therefore, the same message carries over that getting the early time dynamics accurately is especially important for time-dependent PDEs. To summarize, the training algorithm works as follows. For the labeled data, we compute the data loss. And for both the labeled input and the virtual input, we compute the PDE residual loss. And when temporal causality weighting is enabled, we use the causal PDE loss instead. We also compute the initial condition and boundary condition losses. Finally, we take a weighted sum of all these terms and backpropagate to update the model parameters. So in the end, the procedure is given as follows. The data loss where we have labels and physics loss on both paired data and virtual inputs, and optimization to make them cooperate. Now let's move on to the numerical results. And we evaluate physics-informed LNO across a range of operator learning settings, including mappings from initial conditions to solutions, and coefficients to solutions, and forcing terms to solutions, and also multi-conditions to solution settings. Across all benchmarks, we focus on two main questions. That first is data efficiency. So how well does the model perform in the small data regime? And second is out of distribution generalization. That is, how robust is it under distribution shift? Before moving on to the physics-informed results, let me first evaluate the backbone itself. So this slide is purely data-driven results. And here we compare the LNO and advanced LNO and FNO on Burger's equation under the same supervised training setting and evaluate their test errors. The main takeaway is that advanced LNO provides a more flexible architecture than LNO and FNO by decoupling the transient and steady state components. And as a result, it achieves the best accuracy and also the most consistent performance across different runs. Now let's move on to the small data regime for Burger's equation. From here now on, for convenience, I will refer to advanced LNO simply as LNO and the original LNO model as vanilla LNO. Here we compare the data-driven baseline LNO with physics-informed LNO as we reduce the number of labeled training samples, and we use 1,000 virtual inputs in these experiments. The plot on the left shows the test error as a function of number of training samples. And as the number of training samples gets smaller, the test error of LNO rises sharply, showing a clear breakdown in the small data regime. In contrast, a PyLNO degrades much more gradually, which indicates better data efficiency. On the right, I show representative time slice predictions in an extreme low data case. And even with very limited training data of 25, physics-informed LNO follows the reference solution much more closely than LNO, especially in the transient dynamics. So overall, this supports our first main message that physics-informed training with PyLNO substantially improves robustness in the small data regime. Now, let me show the out-of-distribution results for Burger's equation. And in this experiment, we train on initial conditions sampled with the fixed correlation length L train and tests on the case sampled with L test, reporting the relative L2 errors over the grid. For physics-informed LNO, the labeled paired datasets are still drawn only from L train, exactly as in LNO. But the difference is that we additionally generate virtual inputs over a broader range of correlation lengths and use physics-only supervision on them to expand the training distribution. To read the heat map, the bottom left cell corresponds to training on oscillatory data with correlation length 0.5 and testing on the same distribution. By contrast, the bottom right cell corresponds to training on smooth data and testing on oscillatory data, which is much more challenging out of distribution setting. The practical advantage of the physics-informed structure is that when generating virtual input, we can flexibly control the input conditions and target the regimes we care about without having to generate new paired reference solutions. And in these heat maps, that flexibility translates into much stronger robustness away from the diagonal. That is substantially improved out of distribution generalization compared with the purely data-driven baseline. In other words, we get to broaden the training distribution without generating expensive datasets, which is very nice. Next example is Darcy flow, where we mainly focus on the small data regime. Since the overall message is essentially the same as for the Burgers equations, and only the PDE has changed, so I'll keep the remaining discussion brief. The plot on the left shows the test error versus the number of training samples. And as we reduce the number of training samples, the error of LNO increases sharply, while the error of PILNO remains almost unchanged, indicating a clear gain in data efficiency. You may notice that this behavior looks a bit different from Burgers equation, because for Burgers equation, the error of PILNO still increases as the number of data becomes scarce, whereas for Darcy, it stays nearly flat. A plausible reason is that Darcy flow is a steady-state elliptic problem, and in our setup, we also impose the hard boundary constraint by multiplying a modifier. Together, these factors seem to make the physics constraints particularly effective and the training much more stable in the low data regime. On the right, I show a representative prediction in an extreme low data case with number of training samples to be 10. Compared with LNO, physics-informed LNO produces a solution much more closer to the reference and significantly reduces the absolute error. Now let me isolate the effect of virtual inputs on Darcy flow. And as I mentioned earlier, of course, physics can help, but physics-informed training without virtual input can actually underperform the purely data-driven baseline in the small data regime. And this is exactly what we see here. If we add physics losses but enforce them only on the same small training data set, the model does not improve reliably. And in some low data cases, it can even perform worse than the data-driven baseline. However, we train the model with virtual inputs. The picture changes quite clearly that they provide physics-only supervision beyond the paired dataset, which broadens the training distribution and makes the optimization much more stable. As a result, the model becomes far more data efficient and maintains consistently low errors across the small data regime. So the lesson here is fairly direct that physics helps, but only after we give it enough room to breathe. Next, we consider the reaction-diffusion equation. And here we study two settings within the same PDE. So task A is an initial condition to solution mapping, and the task B is a forcing to solution mapping. So this example lets us evaluate physics-informed LNO under two different operator learning tasks in a unified setting. Now, reaction diffusion task A has essentially the same operator setting as Burgers, namely an initial condition to solution mapping. So I will keep this part brief and focus on just out of distribution generalization. And as before, we train a fixed L train and test at L test. And the heat map shows that LNO degrades off the diagonal which means that model performance degrades when trained on smooth data and test on oscillatory data.
Heechang, I have a question which I saw also before, just for the LNO, right? And you, why the case of large correlation length has larger errors? You see the lower row.
Yes.
Has the red colors. You expect for large correlation lengths smaller errors. Why you show in all your plots, in fact, with DeepONet for large correlation lengths, we can actually extrapolate. But here, I didn't expect that the large errors on your training on the left, I would expect those errors to be on the small correlation length, L-train, not the large one.
You mean the right bottom cell or left upper cell?
Yeah, I mean, can you see? I marked it. These errors are for a large correlation length.
Those errors. For
I
them,
expect the other to be the
because I think in this slide,
this has to do with the correlation length. So large correlation length means you don't have the spectral bias, right?
Yeah. I think the lower right cell implements that we train on very smooth data, but we test on
I see it. Because the test is yes, the test is 0.5. Yeah. Sorry.
Yes,
you're right. Yeah.
Thank you. And
I see it. You're right.
Okay, can I move on?
Please do.
Okay. Next, we move to reaction diffusion task B, which is forcing to solution mapping. And the plot on the left again shows the test error as the function of the number of training samples. And as expected, LNO exhibits a sharp increase in errors as the data becomes scarce, whereas PyLNO degrades much more gradually. On the right, in a representative low data setting, physics-informed LNO produces a solution much closer to the reference with a substantially smaller absolute error than LNO. And now let me show the out-of-distribution results for reaction diffusion task B, the forcing to solution setting. And unlike Berger's or reaction diffusion task A, the LNO heat map suggests that this mapping is more difficult to learn with noticeably larger errors across the training test length scale grid. And even so, physics-informed LNO remains quite robust in this setting. The heat map on the right stays consistently low even away from diagonal, indicating that much stronger performance under distribution shifts. So once again, even in this more challenging setting, physics-informed LNO gives a stronger out-of-distribution robustness and strong performance in small data regions. And this slide shows representative predictions for 3 different L-train to L-test settings. And across all of these cases, physics-informed LNO follows the reference solution more closely than LNO. And here, I isolate the effect of temporal-causality weighting on the reaction diffusion problem. And in this comparison, physics-informed LNO uses both virtual inputs and temporal-causality weighting, while physics-informed LNO without temporal-causality weighting uses virtual inputs only. And on the left, we see that temporal-causality weighting leads to faster convergence and a lower final validation error. And on the right, the test error distribution moves to lower values and become tighter, indicating improved accuracy and more stable performance. And you might ask then, what if we apply temporal-causality weight without virtual inputs? And so we repeat the same reaction diffusion setting without virtual inputs. The intuition is that temporal causality weights helps address temporal masking by placing more emphasis on early time residuals, which can improve convergence and stability. But however, in practice, its effect is usually strongest when the physics laws plays a dominant role in training. Virtual inputs naturally create this situation because they add physics-only supervision without introducing additional data anchors. But however, once we remove virtual inputs, the data loss anchors the training more strongly, and the physics loss behaves more like a regularizer. So as a result, the standalone effect of temporal causality weights becomes much harder to see. And empirically, that is exactly what we observe in this figure. And without virtual input, temporal causality weighting can slightly reduce the run-to-run variance, but the gain is much smaller than when it combined with virtual inputs. So in the end, temporal causality weighting can help on its own, but its benefits becomes much more noticeable when it is used together with virtual inputs. And finally, for the first KDB problem, we compared physics-informed LNO, not with LNO, but with DeVos-Mamba. DeVos-Mamba is a very strong model that has shown state-of-the-art performance on time-dependent problems. And for fairness, we use the same first KDB settings as in the DeVos-Mamba paper, which is a multi-condition to solution mapping. As shown in the figure, in the large data regime, DeVos-Mamba actually performs better than physics-informed LNO. However, once we move into the small data regime, DeVos-Mamba also falls into the fundamental limitations of purely data-driven neural operators. So the error increases dramatically as the amount of training data decreases. By contrast, physics-informed LNO degrades much more gradually and maintains strong performance even when the data are scarce. Here is a qualitative first KDB result in the extreme small data regime for 3 input types. And across all cases, physics-informed LNO follows the reference more closely and show clearly lower absolute error than DeVos-Mamba. And let me summarize the main takeaways. So first, physics-informed LNO extends LNO by incorporating PDE, a boundary condition, and initial condition losses, enabling physically constrained operator learning. And second, virtual inputs provide label-free physics-only supervision, which significantly improve data efficiency and out-of-distribution robustness when paired data are scarce. And third, for time-dependent PDEs, temporal causality weighting emphasize early time residuals, mitigating temporal masking and stabilizing optimization. And finally, both virtual inputs and temporal causality weighting are training level mechanisms, so they can integrate it into other physics-informed operator learning methods with minimal modifications. And let me briefly discuss the limitations and future directions. Since incorporating physics losses during training introduce additional computational costs compared to purely data-driven neural operators. And second one, since physics-informed neural networks have developed in a rich set of techniques to improve stability and robustness, so systematically transferring and evaluating additional pin-inspired methods within the operator learning is a promising direction for future works. And our current out-of-distribution study focuses mainly on correlation length shift, so exploring more general ways to broaden the training distribution and to stress test generalization under a wider range of shifts is a natural next step. And finally, our current experiments are conducted on relatively simple domains, so extending the framework to more complex geometries would also be an important and practical and meaningful direction for future work. And if you like more details, the QR code links directly our papers, and it's not a suspicious one, I promise. And those are just appendix to explain. And thank you very much for your attention.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any questions for the speaker from the audience?
Hi, Heechang, this is Suku from Davis. I had a couple of questions. The first one is in terms, it seems that the virtual importance, virtual inputs are the secret sauce, right? It's very important in what you do. So can you just go back? I probably missed it. How are the virtual inputs, like how are they different from the real inputs, right? And based on my recollection, you provide initial conditions through the virtual inputs.
I think these figures
Yeah.
shows well. So
So are
for the
they,
burgers, yes.
probably I can ask my question more clearly. That so for the virtual, if you take initial conditions for some virtual inputs which are randomly created, for example, then you don't have the solution also for those virtual inputs, or you also have the solution?
For virtual inputs, we don't have to calculate the reference solution.
Right. So
and
that's the advantage,
yes.
right? So what does it point to then? You have just initial conditions for different problems, right? But you don't know the
Yes.
solution.
Yes, we don't have to know the solution because we can use as the physics losses to enforce the governing PDE.
Right, but probably I did not get it, but how is it? It's not a, I mean, you just know the initial conditions for a bunch of problems, but I don't know how it's evolving with time, those solutions, right? So if you look at the classical way of doing it, like your real inputs, you have initial conditions and you have the solutions, so you know the evolution, the whole path from initial, the state, right? From initial t equal to 0 to some final t. But for these virtual inputs, you know only what happens at t equal to 0. Is that right?
Yes, we just sample the initial conditions.
Okay. Yeah, probably. Okay. So the second question is sort of related to your weighting factors, how you scale the weights for the L data, for the data loss versus the PDE loss terms, and the decay, right? You have a decay with time increment. So how do you just initialize it to some function with decays with time, or how do you pick those weights?
We can just fix those lambda data. Yes, right. Lambdas. And if you want, you can use it as a adapting weight if you want.
But what you do is not adaptive, right?
Yes, I didn't use adapting weights because without adapting weights, it performs pretty well. And I think we don't need such method to improve more performance.
Yeah, I just want to know, like macroscopically, like what is the ratio of lambda data to lambda PDE, for example, and how critical is that ratio, right? And does it change? Do your results depend on that?
Yes, it depends on the problem.
So then you change the lambda data or lambda PDE. Like in this equation, the L total, right? So you have lambda data, lambda PD, lambda IC, lambda BC.
Yes. For example, for Burgers equations, I think I use the lambda data for about 10, and the others lambda PDs or lambda initial conditions to be 1 or 2 in my memory. Yes.
Yeah, because my intuition will say that lambda data should be much larger, right? Because you're trying to, because that's the ground truth in some sense, right? Because you want to have larger weighting on the data itself compared to the other losses. But I was wondering, just if you choose lambda data as 100 or 1,000, or what happens, right? Essentially,
we have to anchor the data or to predict more precisely.
Right. Yes. Yeah. Okay. Thanks. Yeah. Thanks.
Do we have any other questions for the speaker?
Yes, Heechang, this is Raj. I just had a question on your viscous Burgers equation. So what was the viscosity?
I use viscosity as 0.01 in here. Yes.
That's pretty high, right? That's not a convection equation at all. That is a parabolic equation. So 0.01. So you did not encounter any discontinuity there, right? You didn't try any discontinuous solution, right?
Yes, I usually try kind of smooth solution, and for the discontinuity, I use for on Darcy flow. Its
Okay.
permeability is discontinuity.
Okay. So the permeability distribution is like the one you showed in the bottom figure, right?
Yes,
Okay. Okay. Thanks.
thank you.
Do we have any other questions? Any comments? Okay. Thank you so much, Heechang, for staying up for this presentation. I think it's like almost 2 a.m. in your time zone. And
Yes,
yeah, it's time to move on and start our second session. Thank you so much.
thank you very much.
Our second speaker is Professor Michael Mahoney. He will be giving a talk on machine learning, linear algebra, algorithms for machine learning, and beyond. Professor Mahoney is a professor in the Department of Statistics at the University of California, Berkeley, and affiliated with the International Computer Science Institute. He is also an Amazon scholar and leads the machine learning and analytics group at Lawrence Berkeley National Laboratory. His research focuses on algorithmic and statistical foundation of large-scale data analysis, including randomized matrix algorithms, randomized numerical linear algebra, scientific machine learning, scalable stochastic optimization, geometric network analysis, implicit regularization in neural networks, and physics-informed machine learning with application in genetics, astronomy, medical imaging, social networks, and internet data. Mahoney received his PhD from Yale University in computational statistical mechanics and has held positions at Yale, Yahoo Research, and Stanford University. He has served on several national committees and led major programs and workshops in data science, including activities at Statistical and Applied Mathematical Science Institute, the National Research Council, the Simons Institute for the Theory of Computing, the Park City Mathematics Institute, and the MMDS workshop on algorithms for modern massive data sets. With that introduction, the floor is yours and you can start your presentation.
All right. Well, thanks. And I'm grateful to have the opportunity to tell you about some of the things we've been working on recently. This immediate thing came because I was at ICERM a couple of weeks ago and visited the group there, and we were talking about some things as part of a DARPA-funded project. And so there's two threads in a sense that are coming together. One is I want to develop algorithms where you have strong control on the algorithms. And the other is I want to use the algorithms. And so there's a number of forcing functions here that's sort of good to understand. Historically, scientific computing has provided a forcing function for a lot of high quality algorithms. That's still there, but that dynamic's really changing with a lot of machine learning. And so that's really a first-class citizen providing forcing functions. I mean, the trade-offs in compute and cost and so on is different. And so that's one of the things we want to talk about here. And so the other thread is there's just a lot changing on the hardware landscape also, right? And so what types of algorithms you might want to run and how expensive are they and so on and so forth is different now than a generation ago. So we actually do a lot of work applying these things in scientific machine learning and trying to get a principled, let's say a principled combination of domain-driven models and data-driven models, if you want to call it that. How do you really incorporate physics in sort of a fundamental way that is well posed and plays well with the structure of machine learning, not starting with the one and tacking on the other sort of an afterthought. And so domain sciences view this problem in terms of their verticals. I'm in domain A or B or C. Machine learning is a horizontal that tries to build out horizontal infrastructure, but it gets the traction easiest and earliest on domains where you're relatively ignorant about what's going on, like advertising and social media and computer vision and language and so on. And so I want really to tie the two together. And that's just a basic applied problem. But under the hood, it's an algorithmic problem, because if you're calling certain algorithmic tools that make certain assumptions driven by computational science historically, or driven by industrial level machine learning more recently, they may not play well together. So these are the two backgrounds, and I'll have some slides sort of describing that a little bit. And because things are changing on the hardware side, you get a whole range of opportunities to develop new algorithms. And the problem is, to develop new high quality algorithms takes a lot of effort. You need to know a whole bunch of numerical things. And so the question is, could you machine learn these algorithms? In the sense of, I call a machine learning algorithm to do classification or regression or whatever. That's used to get better classifiers for cats and dogs. It's used to get better GPT for language. It's used for lots of things. Could the output of that be an algorithm, and in particular a linear algebra algorithm, where you have strong control on conditioning and so on and so forth? So that's sort of the background. So I was going to go through a couple slides in a little bit more detail, and then I'll talk about two particular sort of threads where we're doing that. But the high level motivation is that. So one is, in particular on the hardware side, I want to have control on low precision computations. And a very promising thing in this direction is to use randomness. So randomized linear algebra. And this came out of theoretical computer science. It's received attention in scientific computing in the context of low rank approximation, because it plays well with communication and so on and so forth. And if you're on the machine learning side, you might do optimization with stochastic gradient descent, and that doesn't perform so well, actually. So then you used hyperparameterized SGD, or use acceleration, or you use this or that. And a lot of those things are sort of poor man's second order optimization. So can you get stronger control on that? And the elephant in the room there is, there's either an inverse or a linear solve under the hood there, depending on how you want to think about it. And that's hard to deal with memory and so on and so forth. So can you compute it an inverse with just forward solves, just matrix vector multipliers? Because that's of interest in a broad range of applications, and it also plays well with GPUs and heterogeneous hardware and lower precision. And so one of the things we'll be talking about is that, and you may not care, but in other cases you may care about numerical stability and so on. So we want to get strong control on that. So think of it as low precision randomized matrix algorithms to build out sort of the infrastructure for computational math sort of in this modern area, where we need control on conditioning, but we might be working at multiple precisions. Might not mean single quad, single double quad. It might mean single half quarter. So multiple precisions on GPUs. And then the scientific machine learning thread is, I think, sort of a leading order question here is how to combine in a principled way two different things, and think of it as a hard constraint, right? The Euler method is a good method to solve differential equations if you're teaching a class, a 101 class in numerical analysis, but it breaks for all sorts of other things, so discontinuities and hard constraints. And there's a whole career is built around finite volume and et cetera, et cetera. And so how do I learn hard constraints, and how do I learn conservation laws, and can I combine data-driven methods and ML methods, and combine spatiotemporal structure in a principled way? And that's a very non-trivial thing to do, and probably the right way to view that is in terms of hard constraints, in which case you need good control on the underlying linear algebra. Because if you're calling PyTorch, and PyTorch is calling something where you don't have that control, somewhere there's going to be a scale introduced, and some noise scale or some variance scale, and then you're going to be dead. So we want to take a step back and try and understand these things. Let me pause for a second, and then maybe make sure people are sort of still online. And any questions as to the general motivation?
Mike, hi, this is George. I have this morning, we had a visitor here, and he said that NVIDIA is killing the second order, the double precision machines. So Blackwell, they said, I didn't know that, but Blackwell, it's not very good and the next generation will not have. So I think this will come timely if that's true. I don't know if that's true, but that's really. Are you hear about that, or is that true?
So
that's part of your motivation, actually?
I mean, I can spend an hour on this motivation slide, and we can just go over that, because
just one
thing
sentence.
is general framing, the rest is detail. So I think the framing is the important thing, and it's exactly what you're saying. I mean, most people think 10 to the minus 8 is 0, right? And so you go to double precision. 10 to the minus 16 is 0, right? You do numerical stuff to deal with that. And one of the big insights I had was when we were developing matrix algorithms, and I didn't know why they were framing it in a certain way. This was when I didn't know much about blasts and stuff. And they said basically we're framing it because we're doing applied math and computational science or whatever, but we're in an industry being driven by teenagers who play video games. And so you need to jam jam your algorithms into that form factor. And so now NVIDIA is doing these things. It's low precision, it's GPUs because you get this incredible trade-off. It's forward multiplies. There's a lot of work, as you know, I mean, on various forms of QR. In QR, you may make pivot rule decisions where you're swapping columns in and out. I mean, that's incredibly expensive relative to forward multiplies. And so you can't necessarily do the same things you did in the past, but you can do a much broader range of things in a slightly different way. Yeah, so this is exactly the motivation. And I think I'm getting a little bit ahead of myself on some of the motivation slides, but I mean, the best analogy I have is that, in the 70s and 80s, there was a lot of work on trying to standardize algorithms. There's a lot of different types of hardware and architectures and this and that, and even, before RISC. And so the question was, is any of this stuff numerically stable? And I forget the company. I think they hired Pete Stewart to basically say the stuff's not well posed and it'll break. And he's incredibly detailed about the numerics, and he came back with exactly the opposite conclusion. If you do things this way, it's good. And so they're able to standardize a bunch of things, and then they were able to build a certain sort of linear algebraic primitives, BLAS, LAPACK has a bunch of code. And sort of, if you don't know what that is, just thank those people for developing it, right? Anything you call something that calls something that calls BLAS and LAPACK, right? And so, in a sense, we're revisiting that same question because there were certain forcing functions in terms of hardware stuff, and then that drove a lot of hardware development. I mean, I think you're seeing a change, call it a change in the world order, no pun intended. I mean, a change in the world order with respect to computing that you haven't seen in a generation like that, where the demands on the compute and on the applied side, and also the constraints you can do in hardware are very different. And for a generation, I think, to oversimplify, people developed various things in a certain form factor. The machines got 10x faster, but you didn't really have to revisit that form factor because you just waited for the machines to get faster. Now there's a much greater sort of heterogeneity with respect to bit precision and types of hardware going to low precision. And so you need to go back to where we were in the 80s and sort of, rethink through some of that stuff. So the RAND BLAS and RAND LAPACK efforts that we're doing are basically trying to do that, And so a sort of motivating question might be, you go to a numerical analysis book, and a lot of the results are formulated in a way that makes sense if your epsilon error is 10 to the minus 8 or 10 to the minus 16. What fraction of numerical analysis? I mean, just think, the size of the matrix n times the unit round off has to be less than 1. That's sort of a guiding principle. I mean, that might make sense if you're 10 to the minus 8 or 10 to the minus 16. But what if you're 10 to the minus 4 or 10 to the minus 2? You can't work with matrices larger than 100 by 100. So I think you got to go back and so what fraction of numerical analysis works when you're working at half or quarter precision, and going back and reinventing a bunch of that stuff. So I think a good form factor for doing this is exactly this. I mean, ask these questions with respect to forward multiplies and GPUs. Yeah, this is exactly the motivation.
All right, thank you.
Yeah. All right. Okay, so I'll be a little bit more brief because that was a long-winded motivation, but I mean, this is a great plot. We had something AI and memory wall. This plot is 1,000 years old. You see, it's 2021. That's not, and so this is old by these scales. Now it's up and to the right even more. But you see is, the y-axis is log scale. I mean, this is incredible. And so the reason NVIDIA is looking at exactly what you said is because there's a broad range of things, and this is the forcing function for it. And so if we're doing scientific machine learning, this is a fact of the world, and grafting onto that and realizing. So this is the training flops for state-of-the-art models. So you might think these things are wasteful. You might think they're not. That's a separate issue. This is just what it costs. And it's gone up orders of magnitudes, even in the last 10 years or something. We've done a lot of work on quantization. So say we're working at whatever precision we have, lots of times, and so this matters less for QR maybe, when you're swapping columns in and out, but think iterative algorithms, or if you're doing a randomized sketching, or if the data is noisy, you might be able to quantize and go to lower precision. And this could be fixed point, this could be floating point, lower precision. If you're training ML models, admittedly different than scientific computing, but if you're training ML models, those models might need to be. It might be acceptable to quantize them to lower levels of precision at different layers. And so people do that, and they evaluate the quality in terms of forward error, perplexity, or mean squared error, or whatever. is that well posed? Is that backward stable, et cetera, et cetera? So the answer is in general no. What if I quantize a layer to some precision, quantize the next layer to some precision, and realize this is wasteful, and now I want to go to this layer and make it lower precision? Do those things play well with each other numerically? Probably not, right? I mean, if you're trying to propagate backward error and I just change the precision here, existing theory is very conservative and won't work. And so it's a little bit like I have electricity flowing down a wire, and if I change the voltage or frequency, there's an impedance mismatch and something's going to bounce back and be unstable. So I don't think you have the numerical analysis to say if I quantize layers in different ways, things will behave well. So we've done a lot of work on quantization. We have a bunch of things where we're going to take some of the ideas, and the name of this is Pi-Hessian. You can imagine it's related to Python and Hessian. It's a whole bunch around that. And so I'm not going to go into the specifics, but I mean, thinking sort of the sort of so what I'm going to talk about today is mostly the linear algebra algorithms, and can we use ML methodology to learn them? But we're sitting on top of this stuff. A nice use case I like to think about, one is very scientific machine learning, because there, in addition to forward error with errors on cats and dogs, or perplexity of NLP or whatever, I oftentimes want to make claims about the internals of the model, right? There's an ontological statement I want to make about the internals of the model being reliable. And so it's a little bit like, a good analogy is it's a little bit like an ensemble method where I combine things, but I do more than just evaluate the forward error. I really need to respect the structure of the individual experts. And so because this individual expert might be conservation of energy, or might be a physics-informed model here, or might be parameterized neural network, or might be a simulation, and I want to paste them together in an end-to-end way. That's one use case that I'm guessing a lot of you might be familiar with. A different one is the following. Oftentimes people want to make low rank approximations of some type. And so you can do that in one of two ways. You can do that with ridge regression, where A plus lambda I. And essentially what you're doing there is introducing a scale defined by the noise level. And you're saying above that scale is signal and below that scale is noise. And a different way to do it might be to do like a Moore-Penrose inverse, where I just cut at K, I invert on the column space, row space, and below that I zero things out. Okay, so operationally what this might mean is if I construct a left orthogonal factor and a right orthogonal factor, and I put the two together, that operationally might not be exactly Moore-Penrose, but it's a use case, it's a way people develop models that is a little bit like Moore-Penrose. And I could also have a situation where I do an iterative algorithm and I try and drive down the small singular values, but they're not all exactly zero. That's a little bit like ridge. And when I say a little bit like, I mean in the following sense. If I have a hard truncation, what if I'm off by one singular vector? It should be k plus 1 instead of k. There's a very strong instability associated with that, and so that's potentially not good. If I'm only evaluating on forward error, I might not see it, but if I'm interested in the internals of the model, I might see it. The same is actually true if you're using ridge. Ridge softens things out, and so it's more robust in that sense. But if you view ridge not in terms of a statistical prior that says I'm going to write down a Bayesian prior that has a scale of variance and I want to choose that scale, but if I view ridge as a penalty method, where I'm approximating with a soft penalty method the hard constraint of f plus lambda g has to be 0, then what I'm saying is I'm dealing with large values of lambda because I want to choose that g to be 0, and I can only choose it to be 0 if lambda is infinite. And so that problem, viewed as a penalty method, is not well posed for large values of lambda. So I have two ways to introduce scale. One is sort of a hard truncation. One is with a soft ridge. They both introduce scale, and they're both unstable and different. I mean, unstable meaning not well posed, with respect to backward error and inverse processes. So they're both not well posed in different ways. So you could say, could I come up with a model where I don't introduce that scale and I am well posed in some way? And there's various ways to do it, but a lot of them will violate the following. And the following, I think, is a deep sort of principle that's important more broadly, but in particular for scientific ML. So what the following is illustrated on this page. So people have this intuition about low rank, and they introduce scales in lots of ways. If you go and look at matrices, and by this what I'm saying is, look at state-of-the-art trained neural networks. So there's a selection bias. Good engineers tend to release good models. Not always, but there's exceptions that prove the rule, but they tend to. The state-of-the-art models are typically not in science. We see similar things in scientific, but that's much less mature. But computer vision and NLP. We saw this. This is a line of work we started in 2017 when there was 10 publicly available models. 2019, there's 100. 2021, there's 1,000. 2023, there's 10,000. So I'll make a broad statement, and there's lots of exceptions that prove the rule. But basically, state-of-the-art models, if you try and analyze them, quote, scientifically, by which I mean I can't parameterize the theory in terms of stochastic gradient hyperparameters, because Google's not going to give me their compute to reproduce it. I can't parameterize the theory in terms of data, because Google's not going to give me all their data to reproduce their model. So I can only do it in terms of sort of empirical observables. So think of it in terms of physics, right? Things that I can actually measure. One of the things I can measure very reliably is the structure of released models, right? The structure of models that are released. So if you look at trained neural networks, state-of-the-art neural networks, oversimplify a big, long story, everything pre-2013 had a scale. The eigenvalues in particular looked like bulk plus spike, meaning there was something that was very well fit by a random matrix, and then some eigenvalues that stick out. So if you train a 2-layer, 3-layer MLP, MNIST to 99.8% accuracy, you get a bulk plus spike model if you look at the eigenvalues. So I don't have to show you the data. I don't have to tell you the training protocols. I just give you the weights. And empirical fact, the eigenvalues look like a bulk plus spike. And now if you go to a statistician and you say, what do you see when you see random bulk and 10 eigenvectors sticking out? They'll say an obvious hypothesis is bulk plus spike. And so what is a bulk plus spike? Random bulk plus some signal. And a lot of theory and effort is around to pulling the spike out. Good. Every model post 2013, that is false. Every model post 2013 has an eigenvalue spectrum that is heavy-tailed. Think power law to oversimplify. So every model post 2013 does not have a scale, which shouldn't be surprising because the training process is cooking in very strong correlations over many scales. In computer vision, there's a nose, there's an eye, there's a cheek, there's a head, there's a background, right? And so you're cooking in over scales. A little bit analogous to, some of the technical things are different, but a little bit analogous to in equilibrium statistical mechanics, where near critical points, you see correlations, in the variational structure, in the correlational structure that are power law. You see this in fluid dynamics, where you get sort of non-asymptotic regimes and you get singular perturbations, and so you have heavy tails in power spectra or whatever. You see this in a few places, and it's usually a signature that you have some complex internal structure, not some toy thing. So this is, I think, and so you can take this empirical fact and then try and say, oh, maybe I should compute eigenvectors, or maybe I can compute Jacobians, because I said, let's work with empirical data that's released, but of course people want to work with training models, and so they say, well, they want Jacobians and things. So you see this on weight matrices, you see this on Jacobians and other things if you look at the internals of the model, NTK limits, et cetera, et cetera. And then they'll say, geez, I want to compute things. I want to compute the eigenvalue spectra of NTK matrices that are so large I can't work with them. So then you put them into your machine, which is much, much smaller, and then it's still too expensive. So I'm going to do a low rank approximation to approximate it. So you introduce a scale somehow. And it's very difficult to make claims about this matrix when you're working with this thing and you've made those 4 layers of approximation where you don't have a control on the scale. So all this is to say, let's go back. Let's ask very precise linear algebraic questions where we could have control on the scale. So I want to make strong claims about this. So this is really saying, there's LAPAC and that's good. Let's build out core linear algebraic primitives where I have control on these things that are very different than people have historically needed. And we're going to use randomized linear algebra for this. This isn't core to what I'll be talking about today, but it's part of a broader discussion where you sort of put randomness inside the algorithm, not in the data, but there's some formal connections. And if you see the figure on the right, the theory is simplest in which called sketch and solve, right? Just get a sketch and chew on it. If you use that sketch as a preconditioner and call it traditional iterative algorithm, you can get machine precision, 10 to the minus 8, 10 to the minus 16, whatever. So what you're really interested in is this intermediate regime. So I might want a very coarse sketch. That very coarse sketch, think of it as a very rough approximation. But numerical people have a name for rough approximation. It's called a preconditioner. So then you can call a traditional iterative algorithm and boom, just do least squares or low rank and get 10 to the minus 16 with LSRN or LSQR or whatever. What you really want in a broad range of applications now, to this Blackwell comment about NVIDIA, is, well, I want stronger control on in between the two, 10 to the minus 1, 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, and maybe you stop there because you got rid of double precision or something. And so understand this regime better. And so what we want to do is develop better algorithms to get this whole regime right. All right. And I'm getting a little bit tight on time. So we're feeding this into very, particular scientific use cases. For the buzzword foundation is overused. We're trying to do it in as close, apply the ML methodology, train model data and compute on a broad range of data to be a foundation in a capital F sense of the word, not a lowercase f. I mean, really analogous to GPT, where I can take this and I can modify it in various ways. But to do that, we need strong control on the spatiotemporal structure, et cetera. So all the stuff I was talking about we'd need. So I want to talk about two different things. One is going to be Prism, one is going to be AutoSpec. But it's to try and reinvent a lot of this linear algebra, but in the context of the background I was just describing. So maybe I'll pause again because now this is like having a preamble after the preamble, but this is, so is a general context clear? And then I'll talk about Prism and AutoSpec. All right. Okay, so you can forget about all that if you don't care about motivation and you just want to solve two linear algebraic things. You can page yourself back in, but I think it's worth, I wanted to set that because we wanted to be a little bit greedier than just saying I have a better algorithm for Newton-Schultz or for something sort of better iterative algorithm or so on. So, all right, so Prism. So what I put together is two slide decks. And in this business, you need a good name. And so Prism's, I don't know, I think it's a good name. And so it'll stand for something. But what we want to do, this is led by postdoc Shanghao Yang, who's doing a nice job on a couple threads. And this in particular, we want to be distribution free and robust with respect to the input. And I want to compute matrix functions. So this is not QR, it's sort of a little bit higher level. And I want to use it, the motivation will be neural networks, but really there's a matrix function piece and we want control on that. And then with respect to the finer grain things we were talking about. So this and the next paper I talked about is up on the archive last month. All right, so I'll talk about matrix functions. Roughly, these are, you have a function, and you can view it more abstractly, but if I have a matrix A is equal to U sigma U transpose, positive, definite, or whatever, the function of A can be defined to be U, function of the eigenvalue is U transpose. Now, some of the corner cases I was talking about when we want to be sort of robust with respect to introducing scale and so on ways, there's a few corner cases, but roughly think of it as that, okay? All right, so I'll describe some matrix functions. This is something people are doing in NVIDIA. They're trying to train big things. And so I'll describe a case study in terms of the sign, but the sign is just plus minus one. It's a hard constraint. It's a discontinuity. And so some of the stuff I'll be talking about will hold more generally. And then I'll talk about the sort of meta algorithm. And then AutoSpec will be something that's different, but can automate this. So you can think of the two things as separate, but they're complementary. All right. So forget about science, forget about, all I want to do is train big neural networks. All right. So a lot of training algorithms basically repeatedly apply a scalar function in sort of this form. And A is equal to U sigma V transpose. I want to consider a function of A, f of A. And so some of these things are first order, but some of these things really are trying to get finer types of information. So this sort of second order information, let's say. Shampoo is the name of something to get inverse square roots. Natural gradients is doing a first cousin of that. They're getting something about inverses. Fisher information versus Hessian. What's the similarity and difference? One is sort of a statistical concept. One you could define in a matrix. You could define in a function space. The two are related, but slightly different in subtle ways. And so what I'm saying, we're pushing the corner cases. The differences, when we don't push the corner cases, don't matter. But when you push the corner cases, do matter. Muon is the name of something that's gotten some attention recently, dealing with a polar factor, and so there's a polar express, there's a name related to that. Second order layers, you might do some sort of covariance pooling, and you might want to whiten and decorrelate. So a lot of things do something of this form. And so if you go to any one of these papers, it does something of this form, but usually for one problem, for one layer, for one very specific sort of specific setup. So as an example, mu1 will target a matrix, say parameters, and let's say I have this form. So instead of stepping with the matrix M, mu1 will compute sort of a direction update. So I'm doing an optimization. So think of this as a second order optimization. So it's already interesting because I want to do corelinear algebra, and I'm not talking about QR, and I'm not talking about least squares. I'm talking about second order optimization, which could use those things, but I could also treat this as sort of a first class citizen. So if you look at the Rand L. APAC book, that frames optimization over constrained and under constrained just in least squares as a saddle point optimization. And so can you get methods that'll apply to both over constrained and under constrained, and for that matter, just a kernel operation if you had a sort of an implicit matrix multiply and sort of make those all the same or as similar as possible. So we're already talking about something in terms of just optimization, which is a little bit different than, but LAPAC is not all of linear algebra. It's what the snapshot in time that the pain points that needed to be modularized was at the time, right? And so it's not clear that the things that need to be modularized now are the same as 40 years ago. So I think it's worth thinking about this as more of a primitive that we want to optimize and push much lower on the stack. And so instead of stepping with M, mu1 computes this direction only thing. What is this thing? This is looking like a left inverse or something, right? And so I think it was S or some piece of code. What was it? Back 40 years ago, around the time MATLAB was being developed, maybe 50 years ago, had the left inverse as a primitive. And I don't think it's been there since then because I think the numerical people banished it in the 80s. But this is a very nice primitive to think about. Okay, so mu1 produces direction-only updates for weight matrices. It uses a Newton-Schultz polynomial type iteration, meaning it's a bunch of Ford errors. It's GPU friendly, so it doesn't compute the SVD, but does it in a particular way that expresses this as a root. And so I want to think of it as I want to find an inverse. And yeah, I know the rule is you never compute inverses. I could do an SVD and compute the inverse, or I could view the inverse as the root of a matrix equation and then iterate to solve that. All right, so a bunch of existing accelerations, polar express, and so on. They typically require spectral bounds, and those are not known in practice. So that last line is a little technical thing that matters. Say I parameterize an algorithm in terms of some quantity, the smallest singular value or whatever, and I don't know that. So one way to deal with that is to spend a lot more effort to develop an algorithm that approximates that inside the algorithm. Another way to do that is to ignore that, treat that as a hyperparameter, convince people that I need 10x more compute, and then optimize that hyperparameter. The latter is what industry does to first approximation, but it leads to things that are brittle and so on because I don't really have control on that hyperparameter. So we're not going to do that. We're going to try and approximate that internal to the algorithm, which will mean I can take this modularized algorithm and use it in the pipeline more broadly, but it also means you save on compute, and maybe you can do some of this stuff on academic level compute. All right. So which matrix functions matter here? So the expensive part is repeating in a lot of these things, something like the inverse or a polar decomposition or an inverse square root or something for many blocks. You could, if the SVD cost one unit of time step of cost, you could use that, but it doesn't. And it doesn't largely in terms of communication. So you can use randomized algorithms for the SVD, and that's better, but we want to do better than that. And so we want something that's scalable, in particular GPU-friendly or gem-dominant iterations. BLAS 1, BLAS 2, that's a separate issue. But we want something to be, forward matrix multiplication, so gem-dominant. Spectral adaptivity. So we're going to be doing iterative algorithms. So we want that to be more of a sort of a low-level primitive. And so automatic spectrum-aware sort of acceleration across data sets and training stages. And we want it to be pretty general. We don't want to have to go back to polar express and inverse and inverse square root and left orthogonal factors. We want them to be sort of all the same. And so get some primitives that allow us to do that. Okay. So Prism will be that polynomial fitted, randomized, iterative sketching for matrix functions. Okay, so I'll walk you through the details of sign, but there's nothing special about sign. Inverses, left singular, left inverses, square roots, inverse square roots, orthogonal factors, sort of, the iterations are different, but they all fall under the same umbrella. So for matrix sign, and just for simplicity, let's say the spectral norm's less than 1 to remove lots of factors. The sign is a squared, a squared inverse. And I think I'm okay here on matrices, but they might be positive definite on certain slides, but do the usual thing. And we're being careful about the numerical issues. So you can view that as A, then the identity minus A squared, square rooted. Okay, so the point is this is something that I could write as an iteration. And so if these things are numbers, not matrices, go to numerical analysis 101 and I can do a second order root find, and I could find the root. So you can do that if these things are matrices. So Newton-Schultz is, a method, and you can do a Newton-Schultz style iteration derived from the Taylor approximation, and it's in the second sort of gray or blue box here. Start with x naught equals a. Goal is to compute the inverse or whatever the sign, and start with x naught equals a. Apply an iteration. Rk is equal to the identity minus xk plus 1 is equal to xk times some function, f. What is f? F is a degree D Taylor approximation to this quantity, the 1 minus c inverse square root around c equals 0, which is, we get that particular form because of the first box. Other things we want to compute that particular form will be different, but we'll have the same iterative structure like in the second box. So why can classical Newton-Schultz be slow at the start? Second order methods have a funny thing in terms of global and local convergence that I don't want to get into here, but the polynomial can be a poor fit at the beginning, so we just have to be careful at the early stages versus later stages. And we sort of understand why that's the case. So I want to do a fitting, but I want to be robust to this. And in particular, I want to adapt the polynomial to the evolving spectrum of R, because this Rk evolves over time. I mean, you're doing an iteration. I start with A and I want to transform it into the inverse or to the left factor or the step function. So I want to adapt this, and I want to do this without expensive spectral information, right? I don't want to compute this thing. So if you've seen this stuff, you can probably read between the lines and see what I'm doing. If you haven't, just realize there's a bunch of sort of relatively standard stuff we're doing here, right? The key move, we want to replace the Taylor polynomial with a one parameter refit polynomial that depends on the spectrum. This is going to keep the lower order terms in the spectrum, but the higher order coefficients are better fit. And so we get something like this particular prism accelerated Newton-Schultz. This is an exact fit. So x naught equals a, Rk is equal to identity minus xk squared, xk plus 1 is equal to this factor, where G is the solution to this least squares problem. Okay, good. So now I've reduced this to least squares. I'm doing something different, right? I'm computing an inverse or a step function, or a polar factor or whatever by doing an iteration. And in the same way as traditional iterative algorithms, so I'm doing a different problem, but in the same way as traditional iterative algorithms depend on the least squares fit many times, this does too. And that's expensive. This will work, but it's expensive. So now you just take advantage of a notion from randomized linear algebra. This was originally introduced by Petros Straneas and I actually, and it was used in data oblivious form by Woodruff and others. But this is called a subspace embedding. And roughly, if I have a tall least squares problem, I want to project it onto something that roughly preserves the geometry of the low-dimensional space. If you do that, you can solve least squares faster than the traditional algorithm theorem. If you use that as a precondition and call LSRN, you can beat LAPACK, empirical results. And then there's been an arms race in the last 15 years on LAPACK people and randomized people trying to beat each other, and now we're together and we're building this out together. So we're going to do a oblivious subspace embedding basically to solve that least squares problem faster. That'll introduce a little bit of error, but we can still get strong results on the overall iteration. So I'm not going to go into the details of that, but that's sort of what we're doing. So we're doing a forward step with a Newton-Schultz. Each thing boils down to a least squares problem that we're solving with a randomized sort of linear algebra technique. So the general approach is Prism really is sort of a framework or meta algorithm. Express the base iteration in a certain way, and then Prism will adapt the coefficients. So on the left, put the method in this polynomial form. I have a target, x of t. I'm evaluating the residual. I get a degree t Taylor approximation. I'm going to lift to matrices. And so on the right, and then you just accelerate it. So replace the Taylor with a fitted polynomial. Choose the parameters to minimize the next residual, and if it's expensive, as it typically would be, do it with this random sketching technique. All right. Prism uses a structured degree polynomial and so on, and so In particular, this least squares fitting implicitly targets the eigenvalues of Rk. So it'll help that, that early iteration problem I mentioned. All right. Let me just, okay, so high powers, table of numbers. These slides, I don't know if they're on my web page, but I'll put them up so you'll be able to pull them down from that, and the papers are there. So this is to say it works. You can use third order, you can use fifth order, you can do inverse, you can do Chebyshev. There's a whole bunch of things you can do. And this applies for variants of this table, or the expanded version of the table will apply for, all these things listed here, inverses and square roots and inverse square roots and left orthogonal factors and so on. All right, just a couple sort of slides and empirical results to say it works, it does, and we're sort of extending it. But so polar express is something out there, optimizes a polynomial with a predefined singular value spectrum. Assume the eigenvalues are between whatever. What if they're outside that? Again, treat it as a hyperparameter, use up 100x more compute, or learn that during the process like we do. So in particular for polar express, in the paper, they show the final result where they know that spectrum. What if they don't? If they don't, plot here, they can do worse. They can in fact do, the convergence to grades. It slows down substantially, which might not be a surprise, but so Prism is distribution free and will adapt, so it's always better. And so it's comparable, slightly better, or much better depending on the details of the singular value spectrum. It works for polar express. It'll work for all those other things that are matrix functions also. All right. Just in the interest of time, I'm going to not go into the specifics of the accelerate the neural network training, except to say we did it on bulk plus spike. We did it on low rank. We did it on a bunch of matrices from scientific computing and computer vision and NLP. We did it on stuff where it's roughly orthogonal and the eigenvalues decay very quickly. And you get those results you'd sort of expect. An interesting example is, can I come up with a random matrix model where the eigenvalues decay very, very slowly, polynomially, power law, but the elements do not? Because iterative algorithms are defined by these things, right? They're defined by the canonical axes, the elements, and they're really defined by the eigenvalue spectra. And so it's hard to come up with a baseline, a random matrix model where the eigenvalues decay in a power law way and the elements do not. So this HTMP is a high temperature Marchenko-Pasteur. It's motivated by the HTMU, which is that Weight Watcher stuff, the heavy-tailed mechanistic universality. I don't know if I mentioned HTMU there, but that Weight Watcher stuff where we evaluated neural networks and saw that they were all heavy-tailed, we developed a phenomenology called high temperature mechanistic universality. This is a random matrix theorem, a random matrix model that captures that. Empirical, the eigenvalues are heavy-tailed, but the elements are not. And so we evaluated on that too, and you get results. And this is the regime that doesn't introduce a scale in a soft way, doesn't introduce a scale in a hard way, but allows yourself potentially to iterate. And the way to think about this is sometimes the small eigenvalues don't matter. Sometimes they do. If your only tool introduces a scale, of course you're going to say they don't matter. But if you have a tool that can go and explore it and not introduce a scale, that's much more powerful, because sometimes the small eigenvalue is near zero. Think of this as I'm dealing with an operator and I want it to be approximately an operator in a function space, and I want it to be, almost not compact, right? And so then the eigenvalues near zero will have an accumulation point. And so this is a good model for that. And so we stress tested it on that too. And of course, GPT and then Quen and some things, if you're familiar.
Mike, I have a question on the, not the shampoo, but soap, where you work in the soap, you work directly with the eigenbasis. You don't work with the fourth root or the square root. Have you looked at that?
That I don't remember whether we put that in the paper, but we are looking at that. Yeah, I don't remember that when they made it in the appendix of the
because
first
shampoo
paper.
doesn't really work, but soap seems to work. It's expensive, but seems to work.
Yeah,
using directly the eigenbasis.
Yeah, I don't know that that's in the appendix of the first paper. We left it out, and we're looking at it now. But yeah, we are looking at that. Yeah.
Okay, thank you.
All right. A bunch of other evaluations. Okay. Unified view of gem-dominant matrix functions. I think it's a nice hello world, and I'm hoping we can build a bunch of stuff around it, where we want to be careful about the computational math, and do you introduce a scale this way or that way. It's instant adaptive, and so we have control on that, and it uses random sketching in a nice way. And I think, to George, your point, I mean, next year there's going to be SOAP prime, there's going to be something else. This is a nice way to view a bunch of these things and complements and hopefully extends and evaluates. And with luck, industry will take these ideas and eat up compute and do that. But we can also, from the computational or university side, say, this is a nice way to be more fine-grained with respect to stuff we're doing. All right, let me shift gears now and talk about something different. You can page that out and swap something in, but really you should view it as complementary, and I think complementary in sort of an interesting way. I guess, sometimes I take a step back and I wonder, what did you learn from something, right? One thing I guess I learned with AutoSpec is there's this notion of out of distribution in machine learning. And sometimes when you go out of distribution, things fail ungracefully. It's like a non-singular perturbation. And other times they fail sort of gracefully. And so think of it, so that's maybe not surprising from the ML side. Think of it as the penalty method, right? When you do f plus lambda g and you introduce a singular perturbation, that fails ungracefully, but maybe augmented Lagrangian, it's sort of graceful. Within the class of algorithms, it's similar, right? So I could do iterative algorithms for least squares. And some iterative algorithms, like conjugate gradient, if I mess up one or two eigenvalues, it's fine. I just iterate and I need to do 2 or 3 more iterations to pick up those eigenvalues I lost. Other iterative algorithms like Chebyshev's semi-iterative method constructs a polynomial. And if I'm in that regime, it's fine. But if I mess up that eigenvalue approximation, I fail ungracefully. And so we have something here. And what we saw was that because we're trying to learn algorithms, and algorithms are going to be polynomials. If we do it the right way, those polynomials are going to be iterative algorithms. But what if we mess up the distribution? We could fail gracefully or ungracefully, but in particular, we could fail gracefully because if I'm working with an iterative algorithm like conjugate gradient, and you have 2 or 3 directions that you failed to learn because I'm out of distribution, just do a few other iterations and that'll fix that up. So it's a little bit more complicated than that, but there's an interesting space there that, can I view the iterative structure of some of these function space iterative algorithms as a way to learn algorithms and in a way that's robust with respect to outer distribution? Because I don't want everything to completely fall apart when I go from fluids to solids or to a different domain. So AutoSpec, so learning to discover. So now I literally want to discover iterative spectral algorithms. So George, this is one of the things that was with Yannis and Dial. Was directly motivated by that. So I want to discover algorithms. All right. So some of the motivation is similar to what we had before, but think that different domains have sort of different primitive structures that I might be able to exploit. Images, they're 2 dimensions and I might be able to do convolution, and that's a little bit like a spatial filtering. Language has this attention, so it's sort of one-dimensional, but it's a little bit like a relational filtering. And so linear operators, if you think about them, they're sort of iterative matrix functions is a good sort of primitive to think about that way. And so this could be sort of a primitive structure to exploit and then build stuff around. And so I think this might be a framework for constructing iterative algorithms sort of more generally. And so clearly forcing functions ML and NVIDIA going to lower precision and so on. So what fraction of old school computational science can you do? What fraction do you want to do? And maybe you can't do that, but you can do a broader range of other things. All right, so linear systems and preconditioning. Polynomial preconditioners, I've mentioned Neumann and Chebyshev and a bunch of things. Eigenvalue problems, polynomial filters could amplify, I want this top part of the spectrum or the middle part of the spectrum. Matrix functions. I want matrix-free approximations of certain function spaces or different sorts of approximations there. So iterative matrix functions are important in a bunch of places, and I suspect they're going to become more important because of this form factor with being forward compatible with matrix multipliers and gem level sort of operations. So they tend to be communication friendly, hardware friendly, and that's probably going to become more so. Think of the memory wall, right? Matrix-free implementations. This is not just sparse problems traditionally in computational science, but I want to approximate a neural tangent kernel or a conjugate kernel or something else in machine learning. And this could be for NLP or computer vision, but it could be for a scientific ML model. And so I want control on that. And so matrix-free doesn't just mean structured grids from PDEs. It's much broader now, I think. Strong theoretical control and various sort of trade-offs that we want strong control over. I mentioned some of these, whitening and linear solves in ML and second order. Why iterative matrix on the bottom functions are important in ML. So I think you can replace expensive matrix functions with cheap iterative ones. I mentioned that. I can deal with, sort of other types of preconditioning and normalization, which in ML is sort of different. It also implicitly regularizes. So what if I had a black box to do 1 million steps of a power method? And never mind that, the numerical stability of power methods. What if I had a black box that cost 1 step to do 1,000,000 steps of a power method, and that same black box that would charge me for 1 step could do 10 steps of a power method? Which would I want? So namely, does early stopping help? And in a lot of ML use cases, I would want that 10-step version, not the 1,000,000-step version. I would want to not exactly optimize the Rayleigh quotient, but I want to approximate it. Because the 10-step version, you can, informally, and in certain cases, you can make it very precise. Theorem, I exactly optimize Rayleigh quotient that the 1,000,000 steps gives me plus lambda g, where g is a matrix entropy, or g is something else that depends on the form of the iteration. So this having control on this implicit regularization is nice. And so we want to do sort of an automated version of iterative matrix functions, and we want control on these things. So limitations, I think, of a lot of these classical polynomial and rational filtering methods, they rely on exact spectral knowledge. You may not have. You may make CFL or other conditions that give you stuff, but we can't assume that makes sense for ML sort of problems. They tend to be manually derived for each numerical task, and that's a killer, right? The technical debt associated with the numerics is changing, especially in light of hardware and tasks. So you want to be robust to that, sensitive to misspecification bounds and so on. So we want some automated approach to adapt to the observed spectra. So a lot of the classical symbolic methods, I think, in ML, they involve a search over some sort of symbolic space. There's not a lot of structure prior, and it's not really operator specific, right? It's you don't need to know much about function analysis or anything like that. So we want auto-spec discovery to be effective in an end-to-end automated way, conditioned on the operator structure. The operator could be from PDEs or not. It could be from a neural tangent kernel. Matrix free and control on stability. So we have I don't know if this is a final word, but I think it's a good, strong sort of initial hello world. Neural tangent engine, it'll take as input a spectral probe. Think of this as something like you might get in regression diagnostics. It's measures of residual error, or it's other, it's estimates of top and bottom eigenvalues, maybe an estimate of the spectrum or something. And it'll output recursive coefficients representing representing a polynomial, but representing an approximation algorithm, representing an approximate iterative algorithm. So end-to-end differentiable architecture, it resembles NLA recurrences, numerical linear algebra recurrences, but we're not over-optimizing to the traditional NLA form factor, but it's backward compatible with that. Effective, I'll call it self-supervised training, meaning analogous to what you do in natural language processing. In NLP, you don't have labels. And so what you do is you do this self-supervised. You get 10 words and you predict the next word. So you turn this big unsupervised problem into many, many small supervised problems. And so they call it self-supervised. And so we're trying to iterate like that on small synthetic matrices, transfers to large real-world operators with varying sizes and so on. So can you learn on one size and transfer to another size? And a task defined objective enforces desired physical spectral properties. All right. So here's sort of the deployment pipeline for a given X, compute a coarse spectral probe, obtain a recurrence with this engine, meaning an approximation algorithm, and iterate. So we're really doing it. So this is different than Prism, but it's compatible with in the sense that I could get an approximation to Prism, and then I could use this loop to refine it. I could do this loop with other things, but in a sense, this is a way within a reasonably broad class of numerical algorithms to design within a reasonably broad class of numerical problems to design algorithms. So the downstream objective is the problem, and I'm designing an algorithm to solve that. The backbone maps feature coefficients in a particular way using a transition matrix, and the transition matrix will apply these recurrences iteratively. All right. So now you can get into various ways to parameterize things. We used a transition operator parameterized in this way. This is implemented in matrix-free form via matvex with the matrix X. It doesn't need to be matrix-free, but that's sort of almost strictly stronger. This assumes many classical sort of recurrence type structures. Expression is an orthogonal basis generated with three-term recurrence relations, for example. So we can refine and interpolate amongst these sort of templates. So we have a set of primitives and we can expand them out. So what's the learning objective? We use the learning objective to maximize something. And typically the something is performance gain against a baseline method. So, something having to do with a convergence slope. We worked in log scale. You don't need to, but for these particular algorithms, that's the natural scaling. That's done to alleviate bias towards certain spectral profiles. What I mean by that is a lot of ML methods tend to learn. Think of it if you're in images and computer vision, or if you're in a physics-informed setting, low frequency modes faster than higher frequency modes. In certain corner cases, actually, like 2D versus 3D turbulence, that can be inverted. And we have results that show that in state space models, you can move eigenvalues around the complex plane to change that. But most ML architectures and training objectives have a bias to learning sort of low frequency modes, which is faster, which is intuitive. The loss function is a self-supervised design based on learning objective and regularization. This has the F plus lambda G form, the penalty method form, which means that we can't let these coefficients be too large, or we introduce that instability I was referring to before. You could do something else here in augmented Lagrangian to stabilize that, but that hasn't been a pain point so far. The training data are small synthetic matrices with spectral profiles. Sometimes to second order, there's a coupling between the eigenvalue spectra and the magnitudes of the elements. But if we work with matrices but to first approximation, that doesn't matter. So we can train on diagonal matrices. So then the question is, let's get diagonal matrices with interesting distributions. Okay, one is a bunch of eigenvalues, they go to 0 exactly. One is a bunch of eigenvalues, they go to 0 approximately. One is they sort of decay slowly. One is they decay in a polynomial way. So I can go back to that HTMP model. That high temperature Marchenko-Pasteur has a parameter there that I said before we can use that to get eigenvalues that are power law. In fact, I can interpolate between Marchenko-Pasteur and very heavy-tailed, with a truncated power law. So we can use a whole bunch of different versions of that to generate eigenvalues that that could be fed into here. And here, now you're actually training to data that have a heavy-tailed structure. And so the training outcome is generalized to large real-world systems over a range of spectra. So question, what if you train to stuff that has a scale and doesn't, or vice versa? So this is not in the original result, but that's something we're sort of looking at. Okay, so time's almost out. There's a bunch of empirical evaluations we have, and the long story short is that it works. The long story long is, it'll take a little bit more time. So let me not go into details, but I'm glad to answer questions. We can accelerate SPD linear system solves. We can look at matrix square roots. We can take this and couple it with public, shampoo, whatever, but prism, and improve something. We can do eigenvalue filtering of various forms. We, in a separate thread, have a randomized range deflation sort of technique, and you could be interested in the top part of the spectrum or the bottom, or something in between. And so, filter, I want this piece of the spectrum. So AutoSpec, has discovered algorithms using these coarse spectral probes and this iterative structure that can be orders of magnitude faster than, I think, reasonable baselines. We employed this in MATLAB, so it's not low level in RAND-L APAC yet, but on several real world examples and in sort of scientific use cases and scientific ML use cases, and got sort of similar improvements. And so I think the initial paper's out, but there's a whole bunch of other extensions that probably some of you are thinking about, and we're looking at some of those. And then there's some other minimax suboptimality and so on, having to do Chebyshev polynomials. So let me just skip in the sort of interest of time. Okay, so AutoSpec is a neural network training framework for discovering spectrum adaptive iterative algorithms. And it combines sort of a neural network piece, which is sort of relatively straightforward. It's something that ML people would be happy about, and an executable numerical analysis recurrence, which is, I think, reasonably straightforward. And numerical people would say, yeah, that makes sense. And we combine them, and I don't know if maybe there's ways to tweak it to improve it, but I think it's just the right way to get the right trade-off. It provides an end-to-end differentiable architecture for self-supervised training and back-propagating a bunch of numerical tasks that give us much stronger control on things. And it can be trained using small synthetic matrices and then extended to much larger ones. So I think it's gets nice strong improvement in convergence rate and or accuracy, and in particular, not the final word, but much stronger control on the region between 10 to the minus 1 and 10 to the minus 8, right? We want control on accuracy 10 to the minus 2, 4, 6, 8. This is designed for that. Perspectives, a bunch of future directions, quadratic transitions. rational transitions where we want to get stronger control on matrix filters. That's not in the original auto spec, but I talked about that with the matrix sign functional prism. We can do that. Stronger control in first order versus second order. So I think fingers crossed. These two results combined seem like a nice way to do a bunch of things going forward. I think you can implement these ideas in Python yourself. We're actually thinking about reinventing the numerical analysis stack using these randomized techniques. We have the RAND NLA and RAND BLAST book. And so one of the things we did is formulate the least squares problems, as I said, as a second order saddle point. So we could do over constrained, under constrained. If you're under constrained, are you doing more Penrose, are you doing approximate more Penrose, etc. Or square systems where I have a kernel in a matrix-free case. And there's a bunch of things we're looking at. One of them is this, and so we're hoping these iterative algorithms feed into that in a nice way. In which case, we can pull those iterative algorithms much lower in sort of the software and algorithm tech stack, as it were. And a great thing would be in the same way as you're told, organize algorithms with BLAST 1, 2, 3, and just ignore everything else. At some point in the future, that may be true here. We will have a base set of primitives. We pushed everything down, and you can build quadratic programs or whatever on top of it. So numerical linear algebra forms the basis for a bunch of things, whether you're computational science or applied math or AI or ML or whatever. The trade-off points, I think, are very different in terms of precision, in terms of hardware, in terms of forcing functions. We have two things, Prism and AutoSpec, that I think are first, but very non-trivial stabs at going beyond what we were doing before with RAND LAPACK to expanding the convex hull of what's possible low in the stack right now, and lots of connections going forward. So let me wrap up. I'm glad I can stay on a little longer if there's questions, but I want to, if people need to run at the hour, finish up there also. So thanks for giving me the opportunity to tell you some of the things we've been up to.
Thank you. So, yes.
Hi, I'm Young-Kyu. I'm postdoc in Brown. It's excellent talk, and I just have a few questions. So in the first question, in the prism, so you use the polynomial fitting and the accelerate actually beat the classical Moon algorithm, but is there any clue or idea that which order is the optimal for the polynomial fitting? I think usually everyone is using cubic or fourth order, and they don't try the high order polynomial because of the trade-off. But the trade-off means if you use high order polynomial, then it should give us a better better converse rate. But usually for this kind of neural network training, we cannot guarantee that. So do you have any?
Yeah, sorry, I had the noise over there. I was trying to turn it off because I wasn't sure if it was distracting you. Good question. We didn't really address that in detail in the Hello world. We're aware of some of those things. My sense is it's a non-trivial space, actually. So in the same way as sometimes it's better to have a black box for an early stop iterative algorithm than the full thing. Even if they cost the same amount, similarly here, there's a high order polynomials might be more expensive, but it might be better to have the primitives be something lower order, and then have the high order ones be got via some sort of compositional rule on top of it. So what's the right level there, is not something we fully understand yet. So I think that's an open question, yeah. And I think it's different than that, but related. What's the trade-off between polynomials and rational functions or something? Because we want to make sure to cook in a bias that's not just smooth, but because discontinuities matter, hard constraints matter, right? And so is the right way to do that something more analogous maybe to finite volume methods where you have a bunch of things and you think of it in terms of negative viscosities or stuff? Or does it make sense sort of at a more primitive level to put in rational functions, which is a little bit funny, actually, if you think about it, because in a sense, what you might be trying to do is to cook into your dictionary, as it were, not just smooth stuff, but non-smooth stuff. And so I wouldn't be surprised if there's a way to get control on that. So I think that was, people tend to think about that a little bit less, but if there was a way to cook something like that in, and so say I had a fixed budget and I can only do so many things, I might want to have a dictionary of sort of polynomials of some order augmented with a dictionary of these other things rather than a bigger dictionary of polynomials of a slightly higher order. So I think, yeah, so I think there's a lot of open questions there that we haven't fully resolved.
Okay, thank you. And another question is actually for the auto spec. So if I understand correctly, your model will generate the advanced clear-off method because so in that case, it's actually in the framework actual figure, you use the 3-term recurrence or 4 terms or whatever is so if I understand correctly, is a new clear-off method not preconditional for the clear-off method, or it's just a preconditional?
Sorry, what are you asking?
So I mean, so in the CG is using 3-term recurrence using the actually alpha and beta, which means the some kind of the eigenvalues of the matrix.
Yeah.
But in your framework, the neural network will generate some kind of coefficient for the directions. Then it looks like the replacement of the clear-off method, actually replacement of CG, not the preconditioned CG. I mean, AMG plus CG or multigrid plus CG.
Yeah, it could be that. I mean, I could imagine a case where you want to constrain stuff to be compatible with traditional CG, but you also, you might want something to be more flexible. So I could imagine at the software level, you implement that one of either ways, but it could be more general. Yeah.
So is there any how can I say? Is there any dependency on the symmetricity? I mean, for the symmetric problem, the CG is perfect, but for non-symmetric problem, we should use GEMLAS or by CG
Yeah, okay,
stuff.
I see what you think. Yeah, okay. So this was not the hello world sort of results, but there's a big space there. I don't know. I mean, I think yeah, I mean, so that's a good next step or open question. I mean, I think what we tried to do was steal sort of the hello world ideas, the symmetric positive definites a bit easier. I mean, I guess there's some subtleties when you go to the non-symmetric case, and then sometimes there's subtleties if you do min-res, as opposed to other things. If I had to guess, roughly the playbook we outlined here, coupled with the natural numerical modifications, would give similar results. We haven't fleshed that out.
Okay, thank you so much. Great talk.
Hi, Professor Mahoney. This is Raj. Nice talk. Very thought-provoking. So I just had one question from polar express component you showed. So there are two steps there, right? One is for the polynomial. You pre-compute the polynomial, and then second step you just apply those polynomials. So do you prefer both steps to be in the same precision, or you can choose the precision differently?
I mean, the same answer as the previous one. We're looking at that, and I think the answer to that depends on the setup. Where's the pain point? I mean, if one is more expensive than the other, we could do one or the other. I mean, the framework should be able to do one or the other. And we haven't fleshed out that whole design space, but it's an obvious sort of next step. Yeah. We haven't thought about it in the perspective relative to the quantization thread I mentioned very early on, but yeah, I mean, that's a natural question. Yeah, we didn't look at that.
Because I'm asking this question because when you pre-compute it somehow you can cache it, right? And then because that is offline stage, but when the way you choose the precision to cache it, that differs across the different floating point computation, right?
Yeah.
So I think that could also help, like if we can figure out that to accelerate these solvers, right?
Yeah, I mean, I guess there's a general question. I mean, if that's not a pain point, go to higher precision, but it may not be necessary. If it would require 2 extra iterations later on to make up for something. I mean, there's also a subtlety that when you get to lower precision, what does that mean? I mean, are you just sort of lower precision arbitrarily, or did you do randomized rounding, which could be in hardware or something? In which case, oftentimes that introduces a little bit of ridge type regularization because there's a stochastic rounding step. And so, I could imagine I don't, that's fine if I just do some preconditioner and that's a little bit sloppy that I refine later, but I might want that to be a little bit higher quality to avoid that issue. So, I don't know. I haven't thought about that as much, but I don't know that there'll be a general answer to that. It may depend on, the setup,
Okay.
training in, language models versus, vision versus a 3D SciML model versus a 2D SciML. These could be different answers.
Okay. Just one, I just needed your outlook on how do they behave like this for canonical BFGS and the Gauss-Newton approaches, because in those like BFGS, we always strive to improve the condition number, right? So do you have any outlook or some comment for those kind of updates? Like just picking your brain on that. So.
Yeah, so we had done a couple things in the past, and that's a tricky thing to answer, just not for technical reasons, but I just think the standards of different communities are different things, right? Because
Yes.
most optimization people that would know enough about the details, if they send something to an optimization venue, these sorts of things get selected against. And if you send something to an ML venue, sometimes the details of what you're asking get selected against. So I think there's a space, and one of the things I'm hoping is that now that we have a couple of these Hello World results and we have the RAND LA, people could ask that in a meaningful way, because ML sort of has a hard time. They deal with benchmarks, and there's not good benchmarks like that for sort of. You could imagine SciML benchmarks and engineering ML benchmarks and
Yes.
operations research ML benchmarks, where I designed the benchmark to really stress test LBFGS versus other things like you're asking.
Yes.
The community just hasn't done that yet.
Okay.
I would imagine this variance of this, that you could get interesting things there, but I think the communities, that'll be hopefully not too long, a year or two before people get to that. But yeah.
Yeah, but there is a lot of scope in that part of the analysis and benchmarking, right?
Certainly. Yeah, no doubt. Yeah.
Thank you very much, Professor Mahoney. Good to
And it's
see you
not clear
again.
that the answer is that the traditional optimization people, you need to use LBFG, as an example, other things too, ideas, but it's not clear the answers, second order good, LBFGS this way or
Yes.
that way. It's not clear the answers will be the same, even if you need to be aware of that to ask the question, right? If I had to guess, all the evidence suggests the answer will be different than the traditional solution in the past.
Yeah. Thank you very much, Professor Mahoney. Good to see you again. So thanks.
Yes.
Thank you. Do we have any other questions for the speaker? I don't see any other. And also, George had to leave to give a university talk.
Okay.
Yeah, I think we will not
Oh, thank
get.
him. I'm glad to have I saw him a few weeks ago and saw some of you a few weeks ago, but when I was there, but tell him thank you again.
Yeah, thank you so much for your interesting talk. And it's time to close the session. Thank you everybody for joining us today. Have a great weekend.
All right.
Bye.